I would again like to welcome a what I still think of as what I think of as a new one of our new faculty members here at Stony Brook, Owen Rambow. He is a newly hired professor in linguistics and at IAX. You know, he came to us from a company named Elemental Cognition, I believe, and works in natural language processing. And he's going to talk today about natural language understanding and semantic parsing. And do you want questions in the middle, or do you want to wait till the end?
I think questions in the middle, yes, if there's sort of questions or major objections to anything I say, but I might answer.
Okay, that sounds fair. Okay, so I say get started.
Okay, thank you very much. Thank you for inviting me. As Stephen said, I worked at a startup the last 3 years before joining Stony Brook in January. And the talk I'm presenting here is largely based on work we did there, and some of which I would like to continue here at Stony Brook. So what I want to do in the next 50 minutes is sort of start very large, talking about deep text understanding, and then narrowing it to sentence meaning, and narrowing to talk just very narrowly about semantic parsing, which is one type of, which is getting at one type of sentence meaning. There will be a process of getting ever more specific and ever more narrow, which often happens in natural language processing. So this first, which is about deep text understanding, what it is and how do we measure it, is based on an ACL 2020 paper with my colleagues from Elemental Cognition, and the team was led by Jesse Dunyetz. The term machine reading comprehension in the title of that paper basically means deep understanding of text. They're just different ways of talking about the same thing. Over the last, I guess, 10 years, or perhaps even less, a lot of benchmarks have emerged for deep understanding of text, and have their own logos. So I list them here on the left. But the question is, do they actually measure the performance of the system for specific tasks? What exactly are they measuring? And is the types of things that are useful? So specific tasks that we can imagine future AI systems doing are things like answering a question about a clinical timeline in a medical application, perhaps interactively with a doctor, assess compliance with regulation obligations in a legal application, games, read a description of a game world and adjust the character's responses in accordance to that description, or interaction with a robot, read a human's direction and guide a robot to find the item requested. So the outline of this first section is what is missing from these existing texts, how we can analyze stories with what we propose to call a template of understanding, and how state-of-the-art systems perform when we use that kind of evaluation approach based on templates of understanding. I don't want to go into detail here, but here are a whole bunch of existing text understanding benchmark data sets. As you can see, there are really quite a few. There are different types of sourcing methods, going from manually written questions with perhaps with specific instructions from the people who are designing the test set to the people writing the questions that they should be particularly tricky in how they write the questions. Then there are naturally occurring questions, say people asking a bulletin board about how to do X, Y, or Z. There are tests designed for humans, which we can use as tests for machines. And then there are algorithmically generated questions from textual databases. And so there are various types of, problems. They're artificially easy, or there's a focus on a particular type of difficulty which isn't necessarily representative. But important falling of these systems is that they omit obvious questions. So why is that? The reason is that for computers to understand text, they have to understand it at a level view, and a lot of things that we bring to bear when we understand text is common sense knowledge, very obvious inferences, very knowledge we bring to the text based on our common experience and so on. And we expect everyone to have this knowledge and to share it. And we do not include it in questions that we write, or that we write that naturally occur, or that are certainly not in questions designed for humans. However, often these are exactly the questions that machines fall short on, so we need to include them. So our proposal is we want to establish what content systems will need to grasp. For content, we define broadly as information either explicitly expressed in the text or implied in the text, or relied on by the passage in some manner. So what we wanted, so now we'll talk about analyzing stories with a template of understanding. And what we mean by template of understanding is that it is an explicit instruction of what needs to be understood for a particular genre of application relevant text. And the process would be that we start out by choosing a genre, then we characterize what type of info needs to be extracted for that genre. And this is what we call a template of understanding. And then we select text and determine relevant passage content from the text and design the tests for the content. So let me give an example. The genre we chose was stories. We think there are two reasons. First of all, it is useful for many, many different types of applications in the future: legal, medical, social media following, intelligence operations, and so on. Sorry, I need to kill. I'm getting messages from an app here all the time. Okay. And the second reason that we like stories is that there's strong evidence for what kind of content the stories will need to record. And this is based on cognitive science research that investigates how humans understand stories. And this research indicates that human readers attend to 4 areas in particular: the locations of people and things mentioned in the story, throughout the story, the timeline, what is where, when, what event, and what order, causes, and motivations. So motivations in some sense are causes related to cognitive state of the story characters. And we adopt exactly these 4 dimensions that were identified in cognitive science experiments as clusters of questions in our template of understanding. Spatial, where entities; temporal, what event states occur and with what timing; causal, how do, this is a mechanistic notion of causality, how do event states lead to the next events or states; motivational, how do agents' beliefs, desires, goals, and emotions lead to their actions. Here's an example. Here's a story distilled down to a very minor sequence of sentences. One day it was raining. When Allie arrived, Rover ran out the door. He barked when he felt the rain. He ran right back inside. So as you can tell from the story, we worked with children's stories, and we found that even children's stories oriented towards first grade raise a very large number of problems for natural language understanding systems today. So along the spatial dimensions, there would be things like Rover, the dog, is in the yard from when he runs out the door and he runs back inside, and Rover's in the house from when he runs inside until the end of the story. And others as well, like for instance, where is Allie? Temporal is Allie arrives just before Rover runs outside. It is still raining at the end of the story. But the interesting one, of course, is a motivational one. And this will be about Rover. And of course, there's a little caveat here. Rover is actually a dog, and we don't actually understand that much about dog cognition. So we're just sort of projecting human cognition onto the dog here. So Rover runs inside rather than staying put outside. That is the question. Why does he do that? Because Rover has a goal of not getting rained on. How do we know that? Because Rover is getting rained on, and we know that because it is raining. It says so in the story, and when it is raining, things that are outside tend to get rained on, whereas inside do not. And furthermore, we know that Rover does not like getting rained on. That is also not stated explicitly in the story, and here we either use background knowledge about people not liking people and living beings not liking rain, or we might want to interpret he barked when he felt the rain as indication that he's unhappy. And then as a result of having that goal, we infer that he also forms a plan to achieve this goal. If he runs inside, he will be inside. And if Rover is inside, he will not get rained on. So that will achieve the goal. And we can also ask, how does Rover know this last point? We could hypothesize that he reasons that when it is raining, things that are inside tend not to get rained on. So I sort of suspect Rover, the dog, is not performing this kind of inference. So this is what we mean by a template of understanding instantiated for a story. And this instantiated template of understanding we will call a record of understanding. So a record of understanding is an instantiated template. How do we use this in evaluation? So our proposal is that this will be pushed as a way of understanding different types of systems and how they are deeply understanding stories. For our internal use at elemental cognition, we could use the specific knowledge representation that our system output, encode the ROU in that knowledge representation, and then we do just a direct comparison, we call precision type evaluation. But our goal is to do a cross-system evaluation, and we don't want to impose a specific knowledge representation on systems. So the proposal is to do the evaluation based on natural language. So the understanding, as you just saw, is in fact expressed in natural language. And we propose that systems also put out a summary in English of their understanding of the system, of the story, and then human judges can compare the system output against the gold ROU. These would be trained judges typically. One could also envision perhaps seeing if crowdsourcing would do. And there are various ways of making this work, for instance, using the pyramid method of Nenkova and Passano. And this would be in order to account for valid variations and correct answers. There might not be a single way of formulating the ROU, but different ones. And we note that this is very similar in terms of the challenge to the evaluation of other NLP problems, such as MT, machine translation, or summarization, where also you do not have a single correct answer. So there's precedent in doing this sort of evaluation. And in the last section of this initial discussion of deep understanding, I'm going to go through an experiment we did, how a state of the systems fall short on our form of evaluation. The study did use the corpus called the race stories, published in 2017. These are English exams for middle and high school students in China. The ages of the students are 12 to 18, and they're texts and questions. And the texts are exactly the kind of narrative story texts that we are interested in, so it's a very good fit in that sense. The best system in the 2017 paper that introduced the data set on the questions that came with the text was 44% performance, whereas humans did 95%. And in the experiments we do, we use the first two stories from the dev set. Yes.
What was, let's say, random guessing?
Yes, I should know this. I have the result for the experiment. I'll show you shortly. I suspect here there might have been 5 answers. It might have been 20% or something. Yeah. This 44% you'll see in a second is not the state of the art. This is just the performance mentioned of the 2017 paper. So this test set falls in the category of tests designed for humans, of course, with questions written by humans. And the main problem we see is that it omits the obvious questions. So what we did is we turned the test into a multiple choice data set based on our template of understanding. So we used the stories from the test set, but we threw out their questions and created our own questions based on our template of understanding approach. We took the race stories, we have the template of understanding already, we created a record of understanding for each story and listed a bunch of temporal, causal, and motivational content that is crucial in deep understanding of these stories. And then we took that record of understanding and turned it into a multiple choice exam so that we could do our experiment easily. For example, a question like what actually happened when Mr. Green and the man drove together. They came to a small house, which is the correct answer, and then we generated by hand answers that seemed plausible in context and given the story, like they came to a hotel, they traveled around the country, they stopped several times at the side of the road. And we ended up with 201 questions, and we introduced the notion of variant groups, which I'm going to skip in this somewhat accelerated presentation, but it was the notion of variant group as a way of testing for really deep understanding. We used the system XLNet by Yang et al. 2019. It is a transformer-based language model trained on the books corpus on English Wikipedia. And so we used it because it's trained on books. So it is exposed to stories already in the training phase, as opposed to systems trained, say, only on English Wikipedia. And it performed out of the box, trained by us, at a level of 82% on the race task. So first of all, note that it's up 44% in 2 years. And second, note that this is 5% within the top performer at the publication time of the paper last summer. And we basically just did it using an out-of-the-box system. So this speaks to the power of the machine learning approaches that have been developed very recently, that we can just take a system, train it, fine-tune it on the data, provide it, and just do basically within state-of-the-art and much better, like a 2/3 error reduction over published results from 2 years earlier. So this is all good news. But then we asked, how does it perform on our questions? And this is a multiple choice question setup. We aren't asking XLNet to generate the answers. We are just asking it to choose which one. And as you can see here, humans do fine on our questions in the 95% range. XLNet does not. There's a big drop from the 80s down to the 30s. And interestingly, and somewhat puzzlingly, we didn't really investigate why, on the spatial and temporal questions, which seem a little easier in the face of it, both the humans and the XLNet system did worse, whereas causal and motivational, both humans and XLNet did a little better. But overall, XLNet just did way worse than it did on the questions that came with the exam, and it did way worse than humans who did as well on this task, our task, as they did on the original race task. And I did note chance, that chance is lower. So XLNet does do something. It is non-trivial to go from 15 to 37%, and certainly for the causal and motivational from 13 to 38%. So it's not the case that it's just flailing. It has learned something, but it has a long way to go. So let me summarize this question here. We can define deep understanding based on template of understanding. The template of understanding represents knowledge relevant for a given text genre. So I presented a specific template of understanding for stories. For, I don't know, regulatory law text, you would need a very different template of understanding. We did use stories because they are ubiquitous across various applications. And current machine learning technology may produce good results on existing text understanding tests, but bad results on deep understanding tests. And templates of understanding can serve as a basis for a cross-system evaluation, though that has not been implemented or tried at a greater level. And I just got a question on chat. What type of questions is XLNet not good at? So XLNet, so there are two sets of questions. The race data set comes with the questions, which are the questions that the Chinese high school students get as part of their English exam. And XLNet is actually quite good at those questions. And then we created additional questions, multiple choice questions like the race questions, which are based on our template of understanding, which probe the deeper understanding of the test. And that is what these results are. They're based on our questions. So while the system was good at answering questions that the humans are answering that the human students are answering, they are bad at answering the deeper questions that people wouldn't ask humans because people expect humans to know those. That is essentially our interpretation of what's happening. I hope that answered that question.
Do you have a sense of what people would do on a problem like that without the text? So you could imagine you could answer these questions, try to answer the questions without reading the story.
That is, the questions are not designed to make sense. So if you see this question, what actually happened when Mr. Green and the man drove together? Well, you have no idea if you don't know what the story is. So yes, it is all about reading a story and inferring what the answer could be. Does that answer your question?
Maybe. I know I once took the, without going to law school, I once took the multiple choice thing on the bar exam, and I did better than the monkey. And okay. So that's why I'm wondering whether, there are still some clues in just the way people, you assembled your question.
Yeah, it's a good question, and we could have done this test and just reported it here, and we didn't. One caveat is that, so our template of understanding, the way we propose to use a test is not multiple choice. However, we turned it into multiple choice in order to make it look more like the ExcelNet, like the kind of test that RACE is, so that the ExcelNet could be just applied to it as well. If we hadn't done this, ExcelNet would have just flayed is what I'm trying to say. Flailed is what I'm trying to say. So there may have been some bias in the way we created the alternate answers, and this is looking into. However, this is just a small study to motivate the point that current systems don't perform well. So this ExcelNet system that we trained is not our proposed answer to deep understanding of text. So there's sort of a limit to how much time we want to spend on it.
Okay.
So, Owen, I'd like to ask a question.
Yes.
It's pretty striking how you said that the systems do bad on the kinds of questions that seem to rely on the background knowledge that humans have, right? And so I guess the question is do you see one way then of improving these systems to just overtly or explicitly provide this kind of background information in the form of written text? For example, things like, if you go inside, you're less likely to get wet from the rain outside. I mean, do you see that as a potential solution, or what are the problems with that kind of solution?
Yes, that is sort of the crucial question, because I haven't actually been talking about how to solve this problem. I've just been highlighting that there is a problem and how to evaluate it. I think I will have one bullet addressing this on one of the next two or three slides. So if I didn't answer it, ask again. Okay, so that was that first section about deep understanding. Now let me narrow down to aspects of sentence meaning. The idea here is that so far I was talking about the whole text and various types of questions we can ask about that. Now let's ask the question, if we have a single sentence, the idea is that we need to process each of the sentence and build up the meaning of the text going through the text. This is sort of more traditional NLP that is focused on specific tasks, often works a sentence at a time. And the larger claim, and this is I think the answer to Jeff's question, I hope, is that the deep understanding that would solve the problem laid out just now in the previous section would be a sum of, or a combination of the meaning of all the sentences in the text, plus then additional knowledge, which can be classified as common sense knowledge or background knowledge, and some form of inference that combines all of this. So that combines the specific meaning that is found in the sentences in the text and general background knowledge, and somehow can perform inference on it to answer the questions that are being asked in our template of understanding. And this also addresses Stephen's point that sometimes you can answer questions without actually having grasped the meaning of the sentence of the text. If you don't have the text, that some questions are such that you can just answer them using common sense or background knowledge. So in this talk, I will not be talking anymore about the common sense background knowledge and the inference, and that is an active area of research and of particular interest to my colleagues at Elemental Cognition. And I'm no longer at Elemental Cognition, I'm now at Stony Brook. And a lot of this research will not be published anytime soon. So for that reason, I will not be talking more about it. I do want to mention, though, that my colleague Nasrin Mostafazadeh led an effort to collect a database of common sense knowledge using Amazon Mechanical Turk by asking certain types of questions. And she showed that that knowledge was actually useful in making the kind of inferences for stories that elemental cognition is interested in. So there is work in that direction, and there is work in capturing common sense and background knowledge and using it for story understanding, and that is probably the direction to go. Okay, the goal of this section now is to highlight the complexity of the task of extracting sentence meaning. And it is really just a catalog of the kind of things that need to be done, just in order to make clear that this is not a trivial task either, even though we already narrowed things down to a single sentence. So one of these tasks is word sense disambiguation. The same word can have different meanings. John bought a car, that's the buying that has to do with the exchange of money. John bought the story, that's the buying that has to do with the change of cognition. So John now believes that the story is true. Clearly, we can use a context to do the word sense disambiguation, or WSD. The word car indicates that that's a commercial transaction. The word story indicates that that is a cognitive process. And in order to do this in natural language processing, we need an inventory of word senses, and we need annotated corpora, and then we can do machine learning. And this is a very much an active area of research in NLP, and has been for quite a long time. The next kind of task I want to mention is semantic predicate argument structure, the who did what to whom. Here we start out with a meaning for a predicate along the lines that I just outlined in word sense disambiguation. And we ask the question, can we determine how other elements mentioned in the sentence relate to it? So if we have a sentence like John bought a car for $3,000 from his sister, we want to understand that John is a buyer, his sister is a seller, and the price was $3,000. And word sense disambiguation plus this semantic predicate argument structure equals semantic parsing, which I'll be talking about in more detail in the third section. Then there are other tasks, which I will not be talking about, co-reference. This is not strictly speaking at the sentence level, but looks at surrounding sentences as well. It is well known that we need to resolve co-reference between noun phrases, especially pronouns. I give examples using pronouns, but there are other examples using full NPs, like, George Bush and Bush refer to the same person, even though they don't have the same surface form. Sometimes the meaning is clear simply from the grammatical form. So Paul was poor, John bought him a car, or John bought himself a car. Him and himself are not ambiguous. But typically the case is that the grammatical structure or grammatical forms do not disambiguate, as in this pair of examples from Seidner's thesis 79. I took my dog to the vet yesterday. He bit him in the hand. He gave him an injection. Both follow-up sentences sound perfectly natural, and we simply use world knowledge about who's more likely to give an injection, who's more likely to bite, to disambiguate immediately. This is also a very active area of research in NLP, with many annotated corpora existing, also many languages. I just want to mention that event co-reference is a more complex task, something like Liam left for Limerick, his departure devastated us. We need to understand that his departure is the event described in the first sentence. But I will not say more about co-reference resolution. The next thing I just want to mention as a difficulty is quantifier scope disambiguation. This is an area of research very active in linguistics, or at least it was at some point active in linguistics. the scope of quantifiers with respect to each other is constrained by the syntax, but it isn't determined. So if we have a sentence like every student learned a song from a local resident, we can interpret the determiner every as a universal quantifier, and the indefinite determiners a song and a local resident as existential quantifiers. And we end up, if I did the counting right here, with 4 different interpretations. So clearly every student did something, but what we don't know is whether every student had learned a different song and or every student had a different local resident as a teacher or not, or whether in fact there was a single local resident who taught a single song to every student, or a whole bunch of different songs were learned from a whole bunch of different local residents, and so on. This has not at all been a focus in NLP, but it can be important for inference. For example, if we have that sentence there, if we have this sentence, 3 students learned a song from a local residence, and we get the question, how many songs were learned? Well, we need to disambiguate the scope here. And it gets more complex, this problem, if we include an event variable for the event, such as 3 men carried 4 pianos. How many carrying events were there? Well, there could be one where, the 4 pianos are stacked on top of each other, and the 3 men are each grabbing the bottom piano and carrying the stack of pianos. Then there's one carrying event. Or each of the 3 men carried each of the 4 pianos separately. Then we have 12 carrying events, and so on. And what makes this even more complicated for NLP is that it is not at all clear that we as humans always fully disambiguate the scope. So the question is not simply find the right scope, it is find the scope that's relevant to the understanding of the story. I also want to mention implicatures because these are really interesting. Implicature is not a logical inference, but a conclusion the audience can draw from what was not said. So if someone says or writes, I bought 2 pencils, then we can infer that that person did not buy 3 pencils, because if the person had bought 2 pencils, then they would have said so. Similarly, in Sandy is a friend, we can infer that Sandy is not a lover or a spouse, because if Sandy had such a status with respect to the speaker or writer, they would have said so. And so there's a contrast here. If I say, yes, Susan. Slightly worried here that you're going to ask a really difficult question I can't answer.
Well, maybe I am, but I just wanted to ask you, is there any, I'm glad you got to the implicature slide because it's probably the basis for my question. I'm just wondering if there's any place in your template of understanding for a notion of relevance. So if I were to tell you a story and you were to ask me something about a dog getting wet when that was not the point of my story, and it's not really relevant to why I'm telling you the story, that would tell me that you don't understand my, my goal in telling you the story. So I'm just wondering, is there a notion of relevance or a room for a notion of relevance in your theoretical framework?
Yes. When you establish the record of understanding for a particular story, so this is done by humans, they will choose content that they deem relevant. Mm-hmm. So it is implicit, no, it's actually explicitly there in the instructions. There's a long set of instructions how to take the template of understanding, which is general, and a story, and to generate the record of understanding. And part of that is relevance. Mm-hmm. So for example, dogs typically don't get older than 25 years old. So we could include that the dog is younger than 25 years. It's not relevant. Mm-hmm. We will not include it. Yes, absolutely. And of course, then you can have different people have different sense of what's relevant. But that's just this problem I mentioned, that there might be different correct answers. Yes.
So does that mean that if it's in the template, it is therefore relevant?
If it's in the template is the general instructions, what kind of things should be there. If for a specific story, one of the human annotators says, we should put this fact in the record of understanding for the story, then yes, it is relevant, yes. Mm-hmm.
So is there any way to prune that as the story unfolds? So in other words, things become relevant and then are no longer relevant. Is there a...
No. Yes, we worked with stories that are so short that question didn't come up.
Okay, all right, thanks.
But it's a good question. Yep. Yep. Okay, so and just to make the point that these are not random implicatures. If we say Sandy is a Boer or a psychologist or Senegalese, we do not do any inferencing about whether Sandy is a friend, a lover, a spouse, or whatever. So it is very much triggered by the specific choice the writer or speaker makes. And it's based on assumptions about rational conversation and Grace's maxims. And it does contribute important aspects of the meaning of a text or communication. This is not an active area in natural language processing, but there is some formal work on modeling going on that could be used by NLP in the future. And the last point I want to make is modeling cognitive state here. So language does not only convey propositional content, which is what the semantic parsing is about, but also the attitudes of the author towards the propositional content. So let me just give examples using the attitudes of belief and sentiment. There are others, and some examples to illustrate. And suppose we can express belief and sentiment by a number between -1, meaning I don't believe, to 1, I firmly believe, or the speaker firmly believes. So if the sentence is John will leave tomorrow, we infer that the speaker firmly believes that there's no information about sentiment. John may leave tomorrow reduces the strength of belief of the speaker, say to 0.5 or something. And if the speaker says, I hope John will leave tomorrow, we also infer that the speaker is not certain about whether John will leave tomorrow or not. But we do know that the speaker wants John to leave, so there's positive sentiment towards the leaving event. Then there can be report speech like Mary claims John will leave tomorrow. The verb claim implies that the speaker actually doesn't believe what Mary is claiming, namely the leaving event. Whereas Mary says John will leave tomorrow, we actually don't know what the speaker believes about the leaving event, and no sentiment is expressed towards the leaving event. So sentiment analysis, of course, has been a huge area of research in NLP. A lot of the work a bit or very superficial and oriented towards the text, but still there's lots of corpora, lots of work there that can be built on, and some on belief as well. And this is an active area of interest for me that I would like to pursue, but not in this talk. So let's move on to semantic parsing now, narrowing further to a single aspect of sentence meaning. And I will need to speed up a bit. The basic steps in doing semantic parsing are as follows. First of all, we have to choose an ontology, which also comes with argument structure. We determine the content words in the text that need to contribute to the semantic meaning. There's a certain complexity here about multi-word expressions, which I won't talk about again. And then for each content word, we do word sense disambiguation with respect to the ontology that we have chosen. We identify the semantic arguments as text spans or syntactic head words, or perhaps semantic entities. And then we identify the semantic role label, meaning we identify the relationship between the trigger and the argument. And then in theory, semantic parsers are assembled into a single structure representing the meaning of the sentence, perhaps also a larger structure representing the meaning of the text. In theory, so this happens in theory. In practice, it doesn't, just to sort of break up the task a little bit, though abstract meaning representation has in fact pushed in that direction and is interesting for that respect. What is ontology? An ontology is an inventory of everything that there is, that exists out there, and that a text might be talking about, from Greek ontos, being that which is. And it consists of term-designated classes of things or situation or events, things that are, and the relations between these terms. The most important of those is a. So, a car is a means of transportation, or a Mercedes is a car, that sort of thing. Part of a door, maybe part of a car or part of a house. And then additional information, and the most relevant for us right now is argument structure. So if we're talking about, say, giving is a kind of transfer event while someone gives something to someone. There can be other additional information, attributes, objects have a color. There can be typical attribute values. For instance, an elephant is usually gray. But we're really just interested in the argument structure aspect here. And I'm going to briefly present two ontologies that have been used extensively in natural language processing. And I think it's important to understand that these two things, they're often considered rather different types of objects, but in fact, they're both ontologies and share the same function with respect to semantic parsing. The first is PropBank, developed by Martha Palmer and her colleagues starting in 2005. They use a traditional lexicographic approach to word sense, where for each word, they list the senses. And these senses are predicates and called role sets internally in PropBank. And then for each sense separately, the PropBank team added semantic roles, and they are specific to that predicate, to that word sense. There is an attempt to use the same terminology across predicates, so arg0 and arg1 are always intended to refer to the agent and the patient. And the adjunct roles like time, place, and manner, however, are identical across predicates. Here's an example for buy. So we have two role sets, meaning senses for buy, purchase, and accept as truth. These things in italics are just comments. They are illustrating the different meanings that are being brought out. And we see that for purchase, we have 5 roles. They're numbered 0 through 4. There are these dash tags that give a bit more information. Arg0 is a buyer, Arg1 is buyer agent, Arg1 is a thing bought, so it's a patient. And we see the same thing in the other meaning of buy, accept as truth, where Arg0 is the agent believer and Arg1 is the patient thing being believed. But so then we look at this by way of illustrating this, a different word, bring, in the sense of carry along with. We see that arg0 and arg1 have the same interpretation as agent and patient, but look how the direction and goal arguments have been flipped. arg2 is now the goal, it used to be arg4, and arg2, that used to be the direction, direction is now arg4. So, and arg3 is not whatever this is, VSP, I don't even remember. So the important point here is that these numbers beyond 1 do not have meaning across predicates. This is often forgotten in NLP work. And even if we look at arg0 and arg1 and a psych verb like scare, so here now arg0 is a scary entity and arg1 is a scared entity, you know, the dead tree scared Jennifer. Well, the dead tree is not really an agent in the same sense that a buyer is an agent. So even the meaning of agent here is quite weak across predicates. Just to add that as a caveat. The second analogy is FrameNet. This is work started by Chuck Filmer a little earlier in the late 90s. And contrary to PropBank that starts with words, it starts with a situation such as a commercial transaction and then asks how can language express it. And for something as broad as a commercial transaction, there are in fact many ways. There's buy, the verb buy, the verb pay, the verb sell, verb buy with a different argument structure, the verb cost, and so on. So all of these verbs will be grouped together into one frame, the commercial transaction frame. Here it is. There's a definition. There are lots of example sentences. I just show one. Here's obviously a screen grab. And then there's definition of the frame elements. The core frame elements are those specific to commercial transaction. The others are those like time and place that apply to many different frames. Here's a second meaning of buy. Interestingly, FrameNet doesn't present it as accepting a meaning, but actually falling for a meaning. So there's an implicit deception going on. One could discuss whether, you know, buying the idea always implies that someone was deceived or not. That's a separate issue. So here's a quick comparison. PropBank is word-oriented. FrameNet is situation-oriented. PropBank has a small label of row labels, arg0, 1, 2, 3, 4, where FrameNet has a very large inventory of labels because the labels are specific to each frame. And in PropBank, the meaning of the labels, even though they are the same, are not uniform across predicates, whereas in FrameNet, I mean, the labels are already different, so they're definitely specific to frames. PropBank has a very good coverage of verbs and event nouns in several languages. FrameNet has a much worse coverage of verbs and event nouns. And PropBank has lots of annotated text, continuously annotated text, whereas in FrameNet, most of the annotations are single verbs in single isolated sentences. So because of these last two bullets, NLP has favored PropBank in the experiments in the past. We, however, thought that the situation orientation of FrameNet was extremely interesting and corresponded to our goal of deep understanding of text rather than inferring properties of words and text. So we decided to work with FrameNet and to complement it with a second ontology which covers entities, which are not covered very well at all, just dismally in FrameNet. And for the entities, we used NOADS, a New Oxford American Dictionary, to complement it. And the creation vector is work in progress. In the remaining 2 minutes, I want to mention some experiments we did at Elemental Cognition on semantic parsing. Do I have a bit more than 2 minutes, Stephen?
Yes, you have a few more. You have a little more time.
Okay, so this is joint work again with former colleagues, this time led by Aditya Kalyampur. And this is work in progress. So this is the difference working in an academic setting or a company. In a company, the goal there was not to do publications. The goal was to develop internal systems. And if there was something worth publishing, we would publish it. So there was a little less care paid to some methodological issues. So you can call on that, but I just want to warn you. We did a bunch of experiments. The first was purely generative. So we did a comparison of a GP2 language model and the T5 encoder-decoder model. So in this generative approach, we in the fine-tuning, we gave it examples where we gave it a sentence, we marked the trigger, and then we just had the complete solution as a generated text. And this worked surprisingly well. The larger the model, the better. The T5 encoder-decoder model worked better than the GP2 language model. And I have slides here, and you can ask me if you're interested in the detail. But I will go straight to our second experiment where we use multitask learning. So in multitask learning, you have two models that are trained together, but that do different tasks. And the way we set it up then is that we have a first model that takes as its input a sentence and the trigger marked in the sentence, and the sentence also has position numbers, and the output is simply the frame name. So this is the word sense disambiguation task. And in a second phase, a different model trained together with the first model, but a separate model, takes as input the same sentence and the same trigger with the same position numbers, but with the output of the first model, namely the frame name, and outputs roles and spans for those roles. And then the two outputs together are the semantic parse. The ontology we use in this experiment is Hector, and we just use the T5 encoder-decoder model since it performed much better. This is what I mean by the data format. So here are 3 sentences, and we have these 2 tasks. We first have the frame task. So we prepend the sentence with the word frame : to mark the task. Then these numbers are these position numbers I mentioned. And the trigger is highlighted by adding asterisks around it. And then the output is self-motion. So the input is what you see on the left for the first task. The output is that. We have a bunch of sentences that we train the system with. We fine-tune the system with, the T5 system with, and that generates then a system that produces a model that can take this kind of output and produce this kind of output on unseen sentences. And then when we have that, we feed it into this second model, which we trained as follows. We have a different keyword here so that the system can learn different type of output. And we include the frame, the gold frame here in the training. And when we then decode later on, we will include here whatever frame was predicted by the first task. And then this part is exactly the same as above, but the output this time is different. It lists the different roles that this frame self-motion has, such as a self-mover and the goal. Sorry, it lists the different roles that are realized in this sentence. that this frame has, which are just two, the self-mover and the goal. And then it indicates using the indices into the sentence what the span is. So the self-mover is 6 to 9, most of the rest. And the goal is 11 to 14 to the nearest bar. And this is in a system architecture. We have a shared encoder, and it is a T5 encoder, in fact, for the two tasks, but the decoders are different. For the classifier, which we use to choose the word sense, we use a multi-level perceptron, and for the prediction of the roles that is done generatively, we use a T5 decoder. And here are the results. And I'm comparing this to a purely generative approach. We have two different tasks, the frame accuracy task, where we do quite well, and the role task, where we use F1 measure, how many of the roles do we get, how many roles do we predict correctly, we do a little worse in the 80s. And the multitask architecture does a little bit better than the purely generative architecture, so not massively better. So these are pretty good numbers. There's nothing to compare to, but these are experiments on Hector, which is something we created in-house. So in the third experiment, we used the same approach, but did experiments on standard ontologies and data sets. So this here, the input and output is the same approach, but the ontologies we use are PropBank and FrameNet. And we use the T5 encoder-decoder model. For the PropBank experiments, we compared to two existing systems from 2018 and 2019. And we use two systems, our one-stop generative system and our two-step multitask system. The data is just the Connell 2012 data, which covers different genres, I believe. Sorry, I should know that. And we use a standard eval script called Connell eval script. Connell stands for Computational Natural Language Learning. It's a series of conferences. And we use a standard eval script, which, like our previous evaluation that I showed you, is very strict in the role evaluation. You have to get the whole scan exactly correct, and you have to get the role label correct. Here are the results. Again, the current frame accuracy is good. This should not be labeled frame accuracy. This is the complete Connell result, which predicts both the predicate, and it also predicts the role. So this is a complete performance on semantic parsing task. This is mislabeled. So the performance here is in the low 80s. When we use our full generation approach, we also are in the low 80s, but worse than the state of the art. But our multitask result is better than the state of the art, not by much, but by a little bit. In the FrameNet experiment, we again use a state-of-the-art system, which is Swayam-Dipta et al. 2017. As I mentioned, NLP prefers PropBank, so there has been far less work on FrameNet. And we use our two approaches, the full generative approach and the multitask approach. The data set is the standard FrameNet 1.7 evaluation data. And we have two conditions: whether the frame choice, the word sense, is given as gold, or whether that is predicted as well and is part of the problem. And the metric, again, is exact match. And for the prediction of the frame, so this is the word sense disambiguation task, the state of the art, our two systems all do about the same. There is not much improvement. However, if we go to the role prediction, there are massive differences. The state-of-the-art system Sesame is here performing with gold predicates only at the 58% level at F measure. And if the system also is predicting the frame names, it goes down to 52. And we provide an error reduction of about a third. The numbers are not as good as PropBank. This reflects the type of data available for training, and perhaps also the difficulty of the task. It is hard to disambiguate that. However, out of the box, you can see that our systems provide an important improvement over the state of the art in FrameNet semantic parsing. So our T5-based multitask approach beats the state of the art for both PropBank and FrameNet. And what is important in particular for the PropBank results, that this is a much simpler approach. So the state of the art, they developed an ad hoc neural architecture specifically for this task of PropBank semantic parsing. We did not. We just did some fine tuning on a very general input-output format, which we use for PropBank and FrameNet. And using this very general approach and a development time expressed in person months, probably much smaller than the previous state of the art, we can beat the state of the art. We also just happen to do very little parameter tuning, which can often yield better results. I did a quick error analysis and I found that a not insignificant part of the errors are in fact due to problems in the gold standard, because semantic annotation is non-trivial. So let me conclude the entire talk. It's a long way to deep text understanding, but we are at a good place right now to start thinking about how to define the problem of deep text understanding and how to evaluate systems on the problem of deep text understanding. And in the history of NLP, we know that once we have a good evaluation that people trust as really measuring what we want to measure, there can be more rapid development in that area. Even at the sentence level, if we go away from deep text understanding and just look at understanding sentence meaning, we are only starting to cover the full range of meaning we need to access. And there are areas of meaning, especially related to pragmatics and cognitive state modeling, that we are not fully handling yet in NLP. And then narrowing, again, our interest for semantic parsing, we do have good resources and we have pretty good results, but more work is needed, especially if we want to use non-standard ontology, such as FrameNet. In general, there's a point I often make in NLP context, we need to understand what the linguistic resources are actually encoding. For example, this misunderstanding that a lot of NLP researchers have, that the meaning of arg0, arg1, arg2, arg3 in PropBank is the same across predicates. It is not. And perhaps in order to move from the PropBank performance of the low 80s to something higher, we need to focus on this problem that arg2 does not have a uniform meaning. And just to mention my personal goals here at Stony Brook going forward, I want to continue working on the Hector ontology, even though ontology work is not at all sexy in NLP. But I think it's an interesting exercise because, in fact, a lot of the NLP work is using existing ontologies that might be flawed. I want to continue the work on semantic parsing, and I want to expand previous work on cognitive state detection. So thank you very much, and I'm happy to take more questions if there are any.
Okay, thank you. Are there any questions? So, okay, I've got a couple questions. The work on the Hector ontology, is that are you building this ontology in a machine, a machine learning type way, or in a, hands-on annotation way?
So, confession time. So far, it's been entirely hands-on annotation kind of way. This has mainly been the effect of merging two existing ontologies, making choices how to do it. I think the next steps, the interesting part, will be to use machine learning. There has been work on using text corpora to extract ontologies. This has been mainly used in the context of domain-specific ontologies. So we have a domain like, some sub-area of chemical engineering, and we want to learn the terminology that's used here and how it relates to each other. It is a little less clear how we'll deal with language in general. Certainly for sub areas, we could use it. But there's a certain sense that at the top, we want to do this by hand so that we have an organization of the ontology that we trust, and then fill in things from the bottom. So this is an open question. And again, I just want to highlight the fact that all this work on semantic parsing that is being done in NLP, it relies on either PropBank or FrameNet, which were both also entirely created by hand. So it's not like we're doing something different for NLP that other people have done automatically. No, there's always this lexicographic aspect to semantic parsing.
Are there other questions? Okay, how much of this, again, when I think in terms of, okay, I was talking to somebody last night who says that just wait for Google to come out with another language model with 10 times as many parameters. And then these kind of things will be, will be done or better. Okay. And one thing I think that's a problem in, or, these language models are kind of amazing in what they're kind of learning. And is there something here that you're convinced can't be ultimately learned by a language model by the time Google builds a big enough one?
Yes. So the first thing is that even when we're using a language model, so when we're using GPT-2, there is this fine-tuning step. And the fine-tuning step is fine-tuning the language model to perform the tasks that we're interested in, semantic parsing. And how to define the fine-tuning step, there are many different options of doing that. That is not given by the language model. So even if Google increases the size of its language model by a factor of 10 or something, there is still this research question of how do you actually formulate the task in such a way that we can use a language model. Because if you just ask a language model and type in, a sentence and say, give me the semantic parse of this sentence without any fine-tuning, you're not going to get anywhere, right? So it's not the case that the language model on its own solves the problem. It's just that the language model contains so much information that when you fine-tune, you have a higher chance of getting a good result. But the fine-tuning itself is still a non-trivial task. And you saw that we introduced these position numbers in the sentence in our fine-tuning data, and that actually made a difference. So in some sense, people always say that now with all these language models, we don't have feature engineering anymore. Well, that might be true, but we have this fine-tuning engineering. Exactly how to present the data is now, how to present the problem to the language model is an underlying question. Now, a lot of the problem in semantic parsing has to do with things like knowing that horses move and that refrigerators don't move and so on. So, John moved the refrigerator or something, or the refrigerator moved. If we have the sentence, the refrigerator moved, then the refrigerator was not a self-mover. This is sort of knowledge about the world. That's exactly the kind of knowledge that language models do encode, and that's what they bring to the table here. So if we have even more data there, then that might turn out better. They will not solve the tasks. They will not solve our tasks. They will not solve our tasks of cognitive modeling or implicature modeling, because it is up to us as NLP researchers and linguists to define the task, to think about how to formulate it for a machine learning experiment, and to do the experiments to see what works and what doesn't.
Okay, there is another question, Paul. You want to yell it, or you want me to read it?
I can yell it. So when you have question answering, you may have a question that may use multiple joins. Like, for instance, you are looking for actors that played for the director of some movie. So you would need a two hop or three hop. How do machine learning approaches work in these kind of cases?
Yes. So question answering is a particular type of NLP task, which I haven't even mentioned today at all. It is clearly related to everything I've talked about. So if, for instance, we had deep text understanding, we just read all of the text out there and had good inferencing, then we could do complete question answering. And we're basically sort of at the level of human performance. Of course, or even better, because we have access to all this knowledge on the fly. Question answering, however, as an NLP task, which is well defined right now, is different from semantic parsing, because semantic parsing is just getting at the content in this one sentence here. With question answering, the situation is you have a question, you have a bunch of reference texts that are often given, depending on the specific question and task are given already in the problem setting. And then you have to go and find the relevant answer. And often in this kind of multi-hop question answering that you mentioned, you have to assemble bits of information and spit out the result. So I have not worked in question answering specifically. I see it as a particular type of task, which is a little bit different from the task that I've talked about. And if you do have this multi-hop question answering, like, what was your example? Who are the actors who have performed in all the movies of?
Somebody that directed Titanic.
Yeah, exactly. So if, as humans here, we would sort of sit down and have a sequence of tasks that we would perform, look up who directed Titanic, then look up all of that person's movies and form the join of those lists and so on. So yes, so I assume we would want to have a machine learning to perform a similar sequence of tasks. And I know there is work in this area, and as you can tell, I'm not intimately familiar with it. I see it as, I don't see that kind of multi-hop question answering as emblematic of the kind of text understanding problems that we need to solve. That would be something good that we will be able to solve if we solve a lot of other problems, but solving that multi-hop question answering will not mean that we've solved all these other problems. I would see that as an application of NLU technology.
So I have a follow-up question. So what if the text actually describes a sequence of events? You mentioned earlier baby tasks from Facebook, that Paul picks up a ball, goes in the garden, goes then in the kitchen. Where is the ball? In that case, you might need some logical representation of actions. The fact that the ball goes with Paul.
Yes. And yeah, this harks back to the first part of the talk, where this kind of question, where is the ball, is definitely part of the template. Understanding our notion of what it means to understand a text deeply is exactly what you just mentioned. And in order to solve this kind of problem, this is also sort of the answer to Stephen's question, which was not part of this talk, unfortunately, is how to solve this problem, is that we do need this kind of commonplace knowledge, that if someone has an object and self moves to another location, the object has also moved to that other location. That sort of knowledge, which is exactly the kind of knowledge that you don't find written down typically. And a second aspect of this kind of knowledge is the notion of script, going back to the Shankian notion from the 70s and the first heyday of AI, that there are conventionalized sequences of actions, so that if we mention one of them, we can expect others to be evoked and can refer to them implicitly, like the restaurant script is a famous example. I went to a restaurant, the burger was cold. Well, we can figure out what's happening, what the burger is that we're talking about, and what's happened in between going to the restaurant and the burger being cold. And we should be able to answer questions about that as well. So there's this aspect of common sense knowledge. When I have something and move with it, the thing moves as well. And conventionalized knowledge about things like restaurants and other types of culturally conditioned activities.
Thank you.
Susan? I think you raised a hand.
Yes, I did. So, and this talk was so very interesting. And again, I'm glad you brought up Schenk, because not since Schenk have I heard anything quite so ambitious. And it's kind of exciting that AI could return to trying to explain things a little bit better rather than just throwing data at it and hoping the right thing emerges. And so I was just thinking about the flexibility with which stories are constructed. And you can look at human brain imaging research to see when people have an N400 to something odd in a sentence, like the peanut worried that something. So we know that peanuts can't worry because they're inanimate objects that you eat. But of course, people have shown that if you set up like a children's story about the little peanut who had adventures and worried and that kind of thing, then the N400 goes away when you present that kind of sentence to a human. And so is your notion of ontologies or should the notion of ontologies be made to be flexible so that in the world that the story sets up, where you suspend disbelief about whatever, you should be able to swap out the kinds of logical relations to admit certain impossible things for the context of that particular story, but while keeping the other things you need to know, that when the peanut carries its lunch to another room, the lunch goes along with it, or something like that. So that would suggest that you need some kind of nesting of ontologies or ability to be flexible. What do you think? Is that possible with this approach? I mean, again, your approach is so very ambitious that.
Yeah, this is a very good question. Of course, another hard question from Susan. When I was still at All Cognition, we were working on this. We had a corpus of stories, and some came from a publishing company that wrote stories for pedagogical books for kids, and then we needed a lot more, and we asked people who are writers for children's stories, or who are used to who know about what children read. We asked them to write more stories, and we specifically asked them not to include talking peanuts because we knew it would be difficult. So that's just an area we try to avoid. And one of the stories that we used before we asked new stories to be written did include, talking animals, because that is so common in children's stories, and we did have a problem with that. So yes, that is an issue. It will have to be addressed. I assume it's some sort of a coercion going on. There might be different beliefs in different cultures. In some culture it might be natural to talk about the feeling of a tree or something, and in other cultures not. So yeah, there are lots of adjustments that will have to be done in story understanding, and some sort of notion of this is a peanut, but it is acting as if it were a cognitive being, and someone representing that. And so, no, I have no good answer for you, unfortunately.
Okay.
Yan-Hong,
Oh, sorry.
Yan-Hong asked whether the slides are available. I'll be happy to share the slides. I don't know if there's a standard.
Yeah, send me. We post the slides and possibly the video if we can figure this out and you don't object on the AI Institute webpage. So hopefully Owen, send me the slides and we will post them there.
Very good.
And what about the recording too? I have several colleagues from psychology, like Richard Gehrig, who studies story understanding, and I would love for him to be able to hear this talk.
And I would love to hear his feedback, of course.
Okay, Owen, can I put this online?
Absolutely.
Okay, then we will hopefully take care of that. We have been recording it, and hopefully something will happen. Okay. Okay, so yeah, so okay, so I thank everybody for their attention. Our last, thank our speaker, and Ari Kaufman will be our last seminar speaker for this in a month from now, but you'll get an announcement about that. Okay. Okay, so thanks a lot, and we'll see you guys then.
Thanks for the questions.
Okay. Yeah, so Owen, so send